The last conic section I want to take a look at is the hyperbola, and that's what you get when you have a plane that slices through both the upper and the lower nap of the double napped cone. Okay, so for an ellipse, we looked at the sum of the distances from the foci and a point on the ellipse to be a fixed number, but now for hyperbolas, we're going to look at the difference of the distances as being a fixed number or a constant. So let's take a look at what that's going to look like. This is a picture of a hyperbola. It's a set of all points such that if I measure the distance from one foci to a point on the branch, and I measure the distance from that same point to the other focus, the difference between those two will be a constant, always the same. Now you'll notice that we have two branches on a hyperbola, and that's different than what we've had before. And let's look at the parts of the hyperbola. We have what's called the transverse axis. Trans means across, so it's the axis that goes across. Right in the middle, we still have a center. We still have two foci, and they are inside each of the two branches. Now, we always have that distance from the center to the focus, and just like with the ellipse, we're going to call that C. But notice now, C is going to be a larger number than A. A is going to be the distance from the center to the two vertices, just like it was with the ellipse, but in the ellipse, A was larger than C, and now in this case, A is going to be smaller than C. So we have two foci, we've got a center, we have two vertices, we have two branches, and then we also have this which is called the transverse axis. All right, so here we have the standard equation of the hyperbola. X minus h quantity squared over a squared minus y minus k quantity squared over b squared equals 1. This should look very, very familiar. The only difference is that this is a minus instead of a plus. If it's a plus, it's an ellipse. If it's a minus, then it's a hyperbola. Now you will notice in the second equation, it does look different because I have the y quantity listed first and the x quantity listed second. And that really has to do with the fact that these are subtraction, and it does make a difference what order you subtract terms in. For an ellipse, because it was addition, we could just list the x term quantity first and then the y term second. But this, it will make a difference. Okay, now the other thing you should notice is that the a squared here is listed under the x squared quantity, and down here the a squared is listed under the y squared quantity. This distance a that we get from this term a squared is always going to be the distance between the center and the vertex, and sometimes the vertex is going to be on the horizontal axis, sometimes it's going to be on the vertical axis. So something that might be helpful for you to write down somewhere or just remember is that if you have the x quantity listed first here, the a squared, or the a, is going to be a horizontal distance, and so it's going to open left and right. The transverse axis is horizontal, which just means it opens right and left. If the y is listed first, then the transverse axis is vertical, which means it's going to open up and down. So it's going to look more like this. Down here we have the simplified versions because these are centered at the origin. And then this is also an important equation, very important. When we had an ellipse, c squared equaled the difference between our two numbers here, but for a hyperbola, c squared will be the sum of a squared and b squared, so it's the sum of these two quantities. Now you may be wondering, what about this b? I didn't see that in the drawing. I saw the distance A, because that's what we use to get the transverse axis, and I know C is the distance to the focus, but what is this B distance that we used on the ellipse but I haven't seen on the hyperbola? Well, I think the easiest way to see where that comes in is if we would just graph one. So let's do that next. We're going to graph this equation. It's a hyperbola. I know that because of this minus sign. So here are the steps that you go through to do that. Notice that under the x, I've got a 25. That means in the x direction, which is right and left, I'm going to go 5 units. And under the y, I've got a 4, which that tells me that in the up and down direction, or the y direction, I'm going to go up 2 and down 2. But I first need to figure out where my center is. My center for this graph is going to be at the point 2, 3, and that's because we need the opposite of this number for the x-coordinate and the opposite of this number for the y-coordinate. So I'll graph the point 2, 3, and that's my center. From there, I'm going to go 5 units to the right, put a little dot, 5 units to the left, put a little dot, and now I'm going to look at what's underneath my y quantity. That's going to tell me to go up 2 and down 2. Because remember, we are looking at this is my a squared, which means a is 5, and this is my b squared, and that means b is 2. So I'm still going to use those numbers like I did with the ellipse and go up 2 and down 2. But the difference is this is not an ellipse, so I'm not going to draw an ellipse. Instead, I'm going to sketch a rectangle that uses those points. So here's my rectangle. The next thing I'm going to do is connect the diagonals of that rectangle and form what are called asymptotes. Okay, you can see that I've drawn those two intersecting lines. They intersect at the center and they go through the corners of that rectangle that I drew. Those are going to be my asymptotes for my hyperbola. In other words, my hyperbola is going to hug those asymptotes as my values get larger and larger. Now remember that we had said that if the x is listed first, my hyperbola opens left and right. So we'll take and draw that branch to the right. It's going to hug the asymptote, and then we'll do the same thing. We'll draw the branch that goes off to the left, and again it hugs the asymptote. The asymptote helps determine how pointed or how flat the branches are. Okay, so now let's take a look at that box again, because the box gives us some good information. Notice that if I start at the center and go up and over, I can pick out 2 points on that asymptote and I can calculate the slope. I have to rise 2 and run 5. Well, where did those numbers come from? They came from this number and this number. Under the y is the rise, under the x was the run. So if I wanted the equation of this line, I would start with the slope being 2/5, and then I would use one of the points and figure out what the equation is. If I wanted to do the same for this one, I would just look at the fact that I would fall 2, which means I'm going down 2 and then running 5. So the slope here would be a -2/5 for the downward slanting asymptote. So if I needed to, I could find the equation of the asymptotes just using the slope, and the slope is going to come from these two numbers, from my A and my B. If I need to find the coordinates of the focus points, the two foci, then as we have talked about before, when you're finding the foci distances, what you're going to do is you are going to find the sum of these, and then that's going to be c squared. So for this particular problem, I've got c squared equals 25 plus 4. So c squared is 29, which means my distance is the square root of 29, which is somewhere between 5 and 6. So if I were to estimate where those go on my graph, I would go over a little somewhere between 5 and 6. So 1, 2, 3, 4, 5, and 6. Be right about in there, and the same this direction, right about there. Okay, let's do another one. For this particular one, the first thing I'm going to do is figure out my center. And a very common mistake would be for you to tell me that the center is 2, -5. And the reason for that is, notice that this is the y, which means this is the y coordinate, not the x coordinate. So I need to erase that and remember that when I write the center, make sure that the x coordinate is the number that's in the parentheses with the x. So the x coordinate is -5. The y coordinate is a +2. So -5, +2, there's my center. All right, now in the y direction, I'm going to go up 4 and down 4. I'm going to put a little dot. And in my x direction, I'm going to go right 3 and left 3. Next, I'm going to draw my box. And I'm going to draw my asymptotes through the diagonal corners of this box. Okay, now I need to notice that the y squared term is listed first, which means my hyperbola is going to open up and down, which means this is a vertex and this is a vertex. I'm going to draw my branch going up and draw my branch going down. Then we're going to calculate where the foci are by looking at the sum of these two numbers. So c squared is going to equal 16 plus 9. C squared is 25, which means c is 5. That means to find my foci, I'm going to go 5 units, which would put it right here, and go down 5 units, which would put it right there. If I need the actual coordinates for that, I can write that down. I've got, let's 1, 2, 3, 4, 5. I've got -5, comma 6, 7, -5, 7, and -5, -3. That's for both of my foci. And my center is at -5, 2. If I need the slope of these two lines, so let's look at this one first. If I look at my box, I rise 4 and I run 3. So the slope here would be 4/3. If I need the equation for this one, I would start by figuring out the slope. And for this one, I would fall 4 and then run 3 to get from the center to another point on the line. So that would be -4/3. And again, the rise comes from the y's, the run comes from the x's. Here's an equation of a hyperbola that's not in the standard form. Remember that for both ellipses and hyperbolas, this number must be a 1. So in order to get this in the right format, we're going to need to divide all the way through by 9 in order to get that 1. So when I do that, I end up with this as my equation, and now let's graph it. This is a simplified one, and I can tell that the center is 0, 0, because there is no h and k listed, so the center is 0, 0. The x is listed first, which means it's going to open to the left and right, and my left and right distance from center is going to be 3. So 3 to the right, 3 to the left. The number underneath my y is 1, and the square root of 1 is 1. So up and down, I'm going to go 1 unit. I draw my box, and then I draw my diagonals. I've got my asymptotes drawn, and so now I just need to look at the fact that this is an x that's listed first. So my hyperbola is going to open left and right, which means these 2 points are going to be my vertices. I draw my left branch and my right branch, and I'm done. If I need the asymptote, I can pick 2 points on that line and look at the slope as being rise of 1, run of 3. Which means since this goes through the origin, I have the line y equals 1/3 x. And for this one, when I look at my box, I'm going to have a fall of 1 and a run of 3 for those 2 points. So my slope is negative 1/3. So my equation is negative 1/3 x. This will always be the negation of this one. You're going to have a plus or minus 1/3 in this case, or whatever it is, because the box is symmetric, so we're going to have our 2 slopes are always going to be opposites of each other. If I look for my foci distance, then I need to look at the sum of these 2 numbers. So I'm going to have c squared equals 9 plus 1. That means c squared is 10. c equals radical 10, which means radical 10 is a little more than 3. And so my foci are going to go in here, just inside the branches. If I need the coordinates of those, I'm going to have the point radical 10 comma 0 and negative radical 10 comma 0 to get to those 2 points. Okay, here's our last example. We're not going to graph this, we just need to come up with the equation. So when that happens, I don't care if it's a circle, parabola, ellipse, or hyperbola, the first thing you need to do is sketch it so you know which equation to use as your base. So this one says the foci are at negative 1, 2, there's one of them, and 5, 2. Now we know enough about hyperbolas to know that the center is going to be halfway between those two, which is going to be right here at the point 2 comma 2. So my center is 2 comma 2. Next, I'm going to put on my 2 vertices, which are given here as 0, 2 and 4, 2. So 0, 2 and 4, 2 give me my vertices, and because we know that the foci are always inside the branches, my branches are going to be opening like this. And if I know that they're opening left and right, then I know what the basic equation is going to be. My basic equation is x minus h quantity squared, y minus k quantity squared, they're being subtracted, and it always equals 1. And the a squared is always going to be the one that's listed first because it is the one that gives me the transverse axis. Okay, so let's look at some of our numbers. We need to just find a and b. Well, I can see on my drawing that the distance from the center to my vertex is 2 units. So that means this distance, which is a, would be 2. If I look at the distance from the center to the focus, that tells me that c is 3. So remember that we have c squared is always the sum of a squared and b squared for a hyperbola. So 3 squared is going to equal 2 squared plus b squared. So 9 equals 4 plus b squared. B squared would equal 5, which means b would equal the square root of 5, which is, let's say, a little more than 4, so let's just say 2.2. So if I had to graph it, I would use an approximation, but I'm not even asked to graph it. I'm just asked to find the actual equation. So what I'm going to do is I'm going to put my center numbers in here. That was 2 and 2, because my center is 2, 2. I now know that a squared is 2 squared, which is 4, and I know that b squared is 5. I could also say that b is radical 5, so b squared is radical 5 squared, which is 5. So my equation ends up being x minus 2 quantity squared over 4 minus y minus 2 quantity squared over 5. And then the whole thing always equals 1.